Hello, and welcome back to Mechanochemistry Discussions. This seminar series is hosted by NSF-funded Center for Mechanochemical Controlled Chemistry, or CMCC. My name is Mateusz Mariański. I'm one of the center's investigators. As always, the goal of this seminar series is to bring our community together. The seminar streams live on the third Thursday of every month at 11 a.m. Eastern, and they're also available to watch anytime on our YouTube channel. Also on YouTube, you will find all previous speakers that participated in this seminar series, and I encourage you to check them out. We also have some excellent speakers planned for the upcoming month, and we hope that you will join us for all of them. Before we get started, a few quick thank yous. First, Dr. James Batillas, the Center's Director, Jennifer Belzig, the Center's Administrative Coordinator, and two CMCC students without whom this seminar would not happen, Katie Floyd and Ryan Kwok. Please do continue to follow us on our YouTube channel at CMCC and Mechanochemistry Discussions. Before we start, a few quick guidelines. The seminar is being recorded. If you have any questions during the webinar, you can either email them to us at cmccdiscussions@gmail.com, or you can post them directly into the YouTube channel. Either way, they will be propagated to the speaker at the end of the seminar. Without further ado, it is my pleasure to welcome today's speaker, Professor Carsten Bolm from RWTH Aachen Universität. Carsten Bolm was born in Braunschweig, Germany in 1960. He studied chemistry at Technische Universität Braunschweig and the University of Wisconsin-Madison. In 1987, he obtained his doctoral degree with Professor Rietz in Marburg, Germany. After postdoctoral training with Professor Sharpless at MIT, Dr. Bolm worked in Basel with Professor Giese to obtain his habilitation. In 1993, he became Professor of Organic Chemistry at the University of Marburg, and since 1996, he has a Chair of Organic Chemistry at RWTH Aachen University. In 2012, Carsten Bolm became an adjunct professor at Wuhan Institute of Technology, and in 2014, he was awarded a distinguished professorship at RWTH Aachen. Since 2016, he is an honorary professor at Central China Normal University. Professor Carsten Bolm is also a board member of several journals, and between 2008 to 2021, he served as the Associate Director of the Journal of Organic Chemistry. His publication list has about 650 entries, and in 2014, 15, and 16, he was selected Thomson Reuters highly cited researcher. His main research interest is focused on inertial selective catalysis, asymmetric synthesis, bioactive compounds, mechanochemistry, biomass conversion, and sulfur chemistry. It is my pleasure to welcome Professor Bolm to Mechanochemistry Discussions.
Okay, so thank you very much. Thank you very much for inviting me to participate in this conference series. And thanks also for coming to today's seminar. My name is Carsten Bolm, as you heard already, and I will talk about mechanochemistry as an enabling technique for organic synthesis, catalysis, and something else. Now, before I start, I know that you had an introduction already. I'd like to give you a little bit of background and to adjust the scene. So this is a summary from our homepage where you find that we are an organic group. We are preparative organic chemists. We have various topics here in alphabetical order. All of them have in common that essentially we focus on small molecules, so we don't have very big ones, small molecule modifications and syntheses. And one of the topics, and that is here in the center, is actually mechanochemistry. We've been doing mechanochemistry since a while, since a number of years, as you will see in a second. And as a result, we have a big program in mechanochemistry ranging from synthetic organic chemistry, organometallic chemistry, and enzymatic reactions. So we have all kinds of transformations, and a selection of those I will present today. All of that actually has a long history in my group. In 2005, we started with the first proposal to the German Science Foundation, DFG. And because I wanted to participate in a program where we could finally get some money, I asked the question to the German Science Foundation if ball milling, so mechanochemistry, can be useful for asymmetric organocatalysis. And the application was approved. We got the money, and a year later, we were able to publish the first paper on this. In 2006, we described in Angewandte Chemie a reaction that was, I think, initially discovered by Ben List and co-workers, and which is now Nobel Prize chemistry. It's an aldol reaction catalyzed by the organocatalyst proline. And we found that you can do this reaction in the ball mill without any solvent and get outstanding results. The results are as well as in solution, and the common solvent in this transformation is water or DMSO, so very polar solvents. And we could run these reactions in a relatively short period of time without any solvent. So that in the absence of any solvent, we can take a solid ketone, a solid aldehyde, we have a solid catalyst, proline, and we get a solid product. That reaction was surprising to me because I thought that solvation and desolvation effects were very important, but it actually worked very well. It worked also well when we did the steering in a flask protocol, but it took much longer. So essentially, you could also do this without any problem in a little flask. That was no issue, but doing it in the ball mill was much more efficient. In the subsequent years, we focused very much on these transformations, and our colleague Eusebio Lloristi from Mexico, who spent here, I think, 3 months as a visiting faculty, also working in this area. Together with him, we published this Beilstein TV video, which is still accessible online. So I invite you to have a look at this video, which is, I think, describing it very nicely. And also my student, Manuel Llores, he describes it in detail about what he does in these organocatalysis reactions to get good results. So this is, I think, a very interesting video. In the subsequent years, we decided to focus on other transformations, in particular also those involving metals. And this was the first contribution in 2015 when we described a CH bond functionalization under ball milling conditions, under mechanochemical conditions in the ball mill. And this is still surprising to me. We have several papers subsequently with various metals. Now, this is a rhodium catalysis, which I believe was initially described in solvents, in solutions by Frank Glorious. So we don't use any solvent, but if you look at the details, I think it's quite remarkable. We have rhodium, silver, and copper as 3 metals interacting with each other. The terminal oxidant is dioxygen, and we don't use any solvent, we don't use any additional heating, and it proceeds actually very well. The transformation is not perfect. The yields are limited up to 78%, so we don't get 90 or 99 or something. But nevertheless, I think this is a remarkable transformation if you think about the details. And I still don't understand how all these metals interact and how the substrates are transported to the next important intermediate without being transmitted by solvent. So as I mentioned, we have several contributions in this field with various metals. This can be iridium, this can be cobalt, this can be rhodium, and it's always the fact that most of these transformations work actually very well. Some of them work more efficient than in solution. We don't have heating, we don't have solvent, and we have less catalyst. This is more recent chemistry. This is chemistry that we reported on in 2023. And I want to highlight this because it's also a very unusual transformation. This can be done in solution, and we have several contributions by various researchers, in particular in Asia, who described the synthesis of difluoromethyl ethers by difluorocarbene insertions into the OH bond of an alcohol. Now, if you look at this, you realize already this is very unusual. We don't have any solvent. We don't heat. It's a very fast reaction. And also, if you look at the substrate scope, which I will show you, you will note that it is extraordinary because we have primary, secondary, and tertiary alcohols that react. No solvent. Purification is very easy. The reaction conditions are mild. What we actually do is shown here. So this is a solid starting material. We also can liquid starting materials, but this is a solid starting material. We put it in the jar. We add all ingredients. We mill it for 1 hour. We have the crude, as you can see. We filter it and get the pure product. This is extremely simple. We were criticized by a reviewer who said, why did you take cesium chloride? Yes, we took cesium chloride initially because it worked well, but we can also take potassium chloride or sodium chloride to make the mixing easier. So this protocol allows us, as I mentioned, to have a whole range of products. Yeah, this is only a selection to demonstrate that we have primary, secondary, tertiary alcohols. And the last line, actually, I think is the most important one, because it tells us that tertiary alcohols work reasonably well, not all of them, but most of them, some of them. And this is remarkable in the sense that in solution, this does not work very well. So we have something which is, I believe, to be done in the ball mill better than in solution. Now, until now, I have to admit, the chemistry that I described to you could also be done under solvent conditions in solution. Now, you might argue, what is new? Where is organic chemistry progressing under these conditions? We do efficient mixing, yes. We have a very efficient mixing method. We don't have any solvent. We don't heat. Very often we have less catalysts. All of these are advantages of mechanochemistry. But nevertheless, I think the question is what is new? What can you do what can you do that is not possible in solution? So if we can use compression, tension, shear force, impact, these attributes, we might also be able to get unusual reactivity. We might get products which are inaccessible in solution, or at least we do transformations that are impossible to do in solution. Actually, my former postdoc who stayed in Aachen like a super postdoc, Jose Hernandez, who is now a professor in Colombia in South America, together with him, we wrote a perspective already in the Journal of Organic Chemistry in 2017, summarizing transformations giving altered products, pathways which were not possible in solution. Now, subsequently, various other articles were published by others, but I'd like to show you some hints about how this was done and where it was going. The first transformation I'd like to show to you was, in fact, a work that Jose and myself supervised together, and it stems from 2018. And I dig this out because it turned out to be very influential on our current work. It's about the reactivity of a polymorphic catalyst. We all know this polymorphic catalyst. It's Wilkinson's catalyst. We know Wilkinson's catalyst is very prominent in hydrogenation reactions. What I did not know at this stage was that Wilkinson's catalysts consists of two polymorphs. There's a red polymorph and an orange polymorph. They don't distinguish themselves very much. As you can see, there's a slight rotation at one of the triphenylphosphines. Both of them have been characterized in the solid state, and the citations you can see here in 1977. So we know the crystal structures, we know they're two polymorphs, and we wondered, what is the polymorph behavior? So is there any difference in catalytic activity, in catalytic behavior between the red and the orange polymorph? Now, this question cannot be answered, in my understanding, in solution, because in solution, they will form essentially one species, yeah? And then also in the mechanism, you will lose one triphenylphosphine anyways. So you can only do it in the solid state conditions. So we took these two polymorphs separately and analyzed their activity in a reaction with a borane amine adduct. That gives a cyclic aminoborane, a variety of compounds first, and then this goes to the most stable formamide ring and develops hydrogen. Now, we were very pleased to see that this hydrogen development was extremely fast. It's much faster than in solution. Within half an hour, essentially all dihydrogen was released. Unfortunately, to our disappointment, there was no difference between the red and the orange polymorph. Both of them were about the same. So both of them developed hydrogen about the same speed. However, it turned out that when we did the subsequent reaction, the hydrogenation under these conditions, there was a significant difference in one substrate. The trans-stilbene gave the hydrogenation product much more efficiently when we took the red polymorph. The orange was very slow. 13% with the orange, but essentially 99, full conversion almost with the red one. We take the cis derivative. In contrast, the red and the orange polymorph behave the same. I took this example because I believe it cannot be done. This study cannot be done in solution. Yeah, in solution, we will follow the mechanism by Bolm described in the early 70s, where you would lose a triphenylphosphine anyways. I do not have an explanation for this observation. I would love to know why the difference between the orange and the red polymorph occurs, but we could not find out at this stage. So we published a paper, we have a descriptive paper at this stage, describing the facts that these two polymorphs behave differently and that this was a transformation that only proceeds under ball milling conditions. Now, more recent chemistry is described here. For a long time, we couldn't do any sulfur chemistry in the mill. I do not understand why that was the case, but for a number of years, we could not combine our second very important line of research in sulfur chemistry with mechanochemistry. That changed a few years ago, and now essentially we have many transformations that also relate to sulfur chemistry, and this is one of them. So if you do take a sulfinamide and have it reacted under ion catalysis with a dioxazolone, you get a sulfonimidamide. That's the product shown to the right. Release CO2 and get the product. And that works actually very well. It's a single step. We don't have any solvent. We don't have any sensitivity to air, and it's extremely simple in operation. Now, I'm showing this example because we also tried to run these reactions in solution, only very shortly. So we used toluene, we used DCM, and it didn't work very well. This doesn't mean that it doesn't work at all. So we just didn't optimize it for a solvent transformation, but it shows you how efficient you can do these things without any solvent. Yeah, so we do nitrene chemistry, acylnitrene additions to this sulfinamide and get the products. And here you see some examples. And if you come to sulfur chemistry and you realize that this is quite interesting stuff because you get a whole variety of products. This is only a small selection what you see here. So a very nice transformation that proceeds, at least the way we optimized it, better without a solvent. We extended this chemistry recently, published in an Angewandte paper, where we make unusual heterocycles. Now, this is rhodium catalysis. So we have a rhodium catalyst, we have a hypervalent iodine compound, this PIDA, and it cyclizes. It's an intramolecular reaction which combines the nitrogen and the oxygen. It's a very unusual reaction that proceeds without any solvent to give us unprecedented heterocycles. Yeah, so these type of heterocycles were totally unknown. And again, it works actually very well under mechanochemical conditions in the ball mill. So we reach a stage where I can say we do synthesis, we do preparation of organic molecules in ball mills under mechanochemical conditions. And I demonstrated this in the talk here by asymmetric organic catalysis, CH1 functionalization. We applied a polymorphic catalyst and we focused on organosulfur chemistry. What I will do now is to switch gears. Now until now, we formed covalent bonds. We build up molecules, we synthesize molecules. What we do now is we will degrade them. We will specifically degrade them. Now, degradation in under mechanical conditions are known since a long time. I think the very first that I remember, at least from the literature, is from Staudinger, 1934, when he described degradations of polystyrene by pulling polystyrene fibers. And then he described that those fibers and those polymers broke and formed radicals. This is also a degradation process. Now, along these lines, actually, we described something in 2013. We looked at degrading lignin in ball mills. This was a paper that we described, where we described in green chemistry that you can take lignin and even wood. So you can take wood in the ball mill, add sodium hydroxide, start rumbling and isolate the products and get a mixture of products. So we could identify those products. So that was a lignin degradation under milling conditions. And if you look at the literature now, there's a lot of effort in degrading polymers, even PFAS, in the presence of sodium hydroxide. Yeah? So it's very similar to what we did in 2013. So it seems that there's a concept behind it, that you can take polymeric materials and degrade it, in particular with sodium hydroxide. Now, this was a large molecule. It's a rather undefined starting material. But recently, we got attention to another topic. We look at degradations of active pharmaceutical ingredients, of APIs. Now, chloropentogrel is a compound that some of us, maybe most of us, have taken already. It's a painkiller. And we degrade them under milling conditions. So we add an oxidant and silica gel and degrade that API. Now, this API is actually very prominent. And I just went to a pharmacy and asked them, do you have a package of the pill I want to take and give a lecture at the CMCC conference series? So I took a photo of a package. So every pharmacy has this painkiller. And because every pharmacy has it, it must be a very well-known product. And also the impurities in this product are known. So how are the impurities found? Well, pharmaceutical companies have to prove which impurities there are. They would take a solution of this active ingredient and treat it under various conditions with oxidants, reductions, light, heat, and whatever. And then you find these impurities. But if you think about it, this is very unusual because it's very unnatural, because you dissolve this compound in a solvent. In contrast, in the pharmacy would have solid starting material sitting on the bench, and degradation would take a long time, hopefully. So we wondered if we can use and accelerate this degradation process in the solid state by using mechanochemistry. And in fact, we can. So we degrade these compounds to compounds that are shown down here. And I have three oxidants, potassium permanganate, and another oxidant, oxone, is the third one. So we degrade these compounds and we isolate, or we look at least identify, the products that are formed. And the products are not always the same. As you can see here, it depends on the oxidant you take. That's, I think, very natural. And to our delight, first of all, these oxidants are also the ones that you would observe by doing these reactions in solution by standard protocols. But we also observe some which were not detected before. So they might be also a result of the fact that we run our reactions in a solid. So we have much similar conditions than they would occur in a pharmacy, for example, where you have the molecules sitting in the pharmacy with a solid, and you have to wait for a long time, essentially, to get degradation products, which you then can analyze. Now, we do this in half an hour. We degrade these compounds in half an hour and analyze the products that are coming from there. Again, this is a very special case, and we published this in 2021 for the first time. And this concept of accelerated predictive degradations of APIs caught a lot of attention in the pharmaceutical community. But it's, again, a little bit artificial, because here we have the API, the isolated API. So the next step was that we took the isolated API and added excipients. So here are three compounds, painkillers. They all belong to the same class, the thionopyridines, pyridine-related compounds. And for example, Plavix, the first compound you see, has not only the active ingredients, but it also has a tablet core, a coating, a polishing agent. And so it has a lot of different compounds if you think about the individual pill. So in this contribution published in 2023 in ACS Central Sciences, we described the degradation processes of the entire pills, or we added the API to the excipients, and we looked at what is the effect of the excipients. So one example is here. So you take efficient and degrade it with oxone, you get compounds as the major products that were known, but now you also identify products that were unknown under these solid state degradation conditions. So this is, I think, a quite interesting approach, because it gives us an idea about the degradation of these APIs under very realistic conditions that was not possible before. And recently we extended this to sartans. We all know sartans is a very important class of compounds, in particular with the tetrazole. Not all of them have tetrazoles, as you see the last sartan, but most of them have the tetrazoles unit. And we looked at the accelerated degradation of these compounds, and we predicted the compounds that are degraded. And this is one example here. You see losartan, we degrade losartan, and you see the tetrazole is degraded, or the methyl alcohol is degraded, either oxidized or lost entirely. So we have the profile of degradation products in a very short period of time. So I think this is quite an interesting approach, where we now use degradation studies for predicting the profiles of degradation of APIs. Okay, we talked about preparations, we talked about degradations, and in the last part of my presentation, I'd like to mention a branch of our chemistry that goes to molecular recognition, whereas the preparation and degradation was related to covalent bonds. This is more associative. Yeah? So we look at supramolecular chemistry, at least, when you think about this. This topic has a background from two sides. In fact, we had a collaboration with our company here in Aachen, Magritech. They have the benchtop NMRs, and we looked at accelerated sublimations. So molecules were sublimed in the mixer mill. You can see, I have a laser pointer here. You can see this is the mixer mill. They sublimed, and continuously we looked at the behavior of these molecules by using solvent-based NMR spectroscopy. Now, the second line for coming to this topic that I will describe to you stems from my colleague Thomas Wiegand. He was hired 2 or 3 years ago in Aachen, and we immediately realized that we are a dream team, if you like, because he does solid-state NMR spectroscopy, something that is extremely helpful if you want to study the product composition of a mechanochemical reaction. So these two projects actually have something in common, and they have a common starting material. This is trifluoromethylactic acid, a chiral compound that exists in 2 enantiomers. So we have the S enantiomer and the R enantiomer. And that played a dominant role in the sublimation process, but also became a tool in the studies with Thomas Wiegand. This compound is a very prominent compound, and it was heavily studied by our colleague Vadim Soloshonok, who is now in the Basque country. This molecule has a very unusual behavior because it has a process that is called an optical self-purification. What does it mean? Well, you have a compound composition that is 60% of enantiomeric excess. You put it on the bench, go for lunch, and return, and you come and have a product composition of 90% EE. So it seems to increase the enantiomeric excess. Perhaps you can argue, well, maybe you lose some of the material by subliming the racemic composition. Yeah, so you change the enantiomeric excess to self-purify this compound, or this compound self-purifies itself. This behavior has been studied by Soloshonok extensively, and one reason for it might be that the racemic crystals have a different form compared to the enantiomeric, or to the crystals of the enantiomeric starting materials. So if you crystallize S-TFLA or R-TFLA, the crystals have a different form than the racemic crystals from R and S-TFLA. That is also expressed by the PXRD pattern, which differ. They're not the same. So because the PSRD pattern are different, we wondered, how about the solid state NMR spectra? If you have two different types of crystals, also the solid state NMR data, the chemical shifts might be different. And in fact, they are. So if you look at the chemical shift of the S or the R TFLA, you find a signal in the carbonyl region, which is a different position than the racemic, than the one of the racemic TFLA. Now that's a good sign, because that allows us now to distinguish between enantiopure crystals and racemic crystals. It turned out that this method is actually so precise that we can use it for the determination of the enantiomeric composition. There's a clear line and a clear relationship between the chemical shift. You can analyze it, you can run the integral of it and determine the enantiomeric ratio and the EE of the product. Now that is very nice. So that was the first step. And I was very surprised that this is possible by solid state NMR. But actually we can do one step further. So knowing now that we have the analytical tool to distinguish between the crystals of enantiopure material and the crystals of the racemic material, we wondered about the influence of milling and mixing. Can we determine how strong a milling effect is if we use a mixer mill, a resonant acoustic mixer, by analyzing the composition of TFLA? So the idea is that we form a conglomerate between crystals of S and R. We very carefully grind it, we very carefully mix it. No, don't grind it, mix it. And then we used a mixer mill or resonant acoustic mixing or a press and try to determine how much of the racemic crystals are formed. So what is the impact of the mixer mill and the resonant acoustic mixer, for example? That's what I want to show you. So let's start with the mixer mill. So this experiment shows you that mixer mill is extremely efficient in forming racemic crystals from an artificial conglomerate composed of R crystals and S crystals. So you see the chemical shift of the pure enantiomers of the racemate, the third line from the bottom. And if you grind R and S together for 30 seconds in the mixer mill, you get immediately formation of the racemate. It's a very, very efficient way of getting the racemate. And for me, this is remarkable because we have R crystals and S crystals. We bring them together, and within 30 seconds, we have essentially only racemic crystals formed. This is different if we run the experiment in a resonant acoustic mixer. So in the resonant acoustic mixer, we don't need 30 seconds. We need more time. We need minutes. So we run this experiment for 20 minutes. And what you find here is that the formation of the racemate is very much dependent now on the force, the G force. That instrument that we have has 100 G as the maximum, and that's the most powerful one, and then it's shorter in time. And it also depends on the form of the crystals. So if you pre-mill the two enantiomers before putting them in the resonant acoustic mixer, they react much faster. So a pre-milled material is reacting faster than a non-pre-milled material. That expresses the curves here. But it's much less efficient. So that is interesting if you look at TFLA, but TFLA is also very artificial. So we have very artificial starting materials with very special behavior. It's too special, essentially. So we wondered about amino acids. It's also of interest for the prebiotic chemistry, for sure. Do amino acids show the same behavior? And can we do the same, can we follow the same trend by using amino acids? Well, we've done so in this paper that we published last year with alanine and serine. And what I will show you are the results from serine, but alanine are analogously. So we know that serine differs in the solid state structures of racemic serine and enantiopure serine are different. So here's the solid state structure of DL serine and L serine. You see a clear difference. So they differ. That's good. And we wondered, well, how about the solid state NMR? And also the solid state NMR differs. So if you take the solid state NMR from D-serine and Rex-serine, you see a difference. A chemical shift difference in the carbonyl region and also in the alpha and beta carbon region. So that's good. So we can do the same as before. We can study the impact of milling and resonant acoustic mixing. If we put the two enantiomers in a mixer mill and mix for 20 minutes, we see racemate formation. And that's very clear, as you can see from the green line at the top. Yeah, so these two enantiomers, again, find each other and form the racemate. It's not as fast as in TFLA, where it was 30 seconds. We need 20 minutes, but nevertheless, it's possible. How about the resonant acoustic mixing? Well, in this paper in 2024, at the end of 2024, we described that no racemic phase was observed. And that, in fact, is still valid under the conditions that we described, because we did it without any solvent, and it indeed did not form a racemic phase no matter what we did. The situation has changed now. So now we know what to do. We know now that little traces of solvent can change the situation tremendously. So now I would say this result that we described in this paper correctly can also be modified in the sense that we now know how to form racemic compounds also in the resonant acoustic mixer. So now we learn more from the previous experiments, and we proceed in this chemistry, which is really exciting because we have many amino acids to look at, we have many conditions, and we have many things to do. And I'm very grateful to my colleague Thomas Wiegand about this collaboration, which really advances also on the chemistry and the thinking. Now that brings me to the end of my presentation. I described to you some chemistry that we have followed. We are a synthetic organic group, so we do preparative organic chemistry, and that can be the full screen. Yeah? So I selected a few examples from organocatalysis, from CH bond functionalization, from polymorphic catalysts. But we also started to look at degradation. So degradation of APIs in particular, how do they degrade? And that, as I mentioned, I think is significant for pharmaceutical industry. And the last one was a playground that particularly was developed in the collaboration with my colleague Thomas Wiegand. And it's pleasing to see how we get fundamental understanding by using the different milling techniques and the various ways of getting reactions to go. And they don't have to be covalently bond. This is also mechanochemistry, where we have supramolecular arrangements analyzed by the techniques. Finally, all of that is only possible because it's a dedicated group. This is the group as it was, I believe, last year. About half of them work very focused on mechanochemistry. The other have other topics, including sulfur chemistry and the topics I mentioned before. I'm very grateful to them that they work so hard and discover new things. And finally, I'd like to thank you again for your kind attention. I'm very happy to participate in this CMCC conference series, and I appreciate the invitation. Thank you very much for your attention.
Thank you very much, Carsten, for your presentation. We have several questions from the audience, so let me ask you a few of them. So the first question is that many of the examples of the reactions that you've shown here, you show only the formation of the products. Do you have any thoughts about the effect of the ball milling on the reaction mechanisms? And yeah, what's the effect of the ball mill on the reaction mechanism itself? And is it just a mixing technique, or there is an effect of the force acting on the mechanism?
Wow, that's a very central question, and I think we could have many seminars on this. There's all facets, I would say. Very often, I believe the mechanism does not change necessarily. So we had one transformation. It was a CH bond functionalization where we studied the isotope effect, the deuterium isotope effect. And there was a different number, and I was very excited about it. until my student noticed, well, you know, the reaction conditions are so different. It's no surprise that we have a different isotope effect. And I fully agree. So I believe that most of the time, the fundamental mechanism itself is not changed. The chemistry is the same. However, we have factors which are dominated by crystallinity, by a formalization. Yeah, so the solvent might play a role also in the mechanistic scheme, and then you will have different pathways leading to different products maybe. So to give a general answer is very difficult. I would say the fundamental mechanism might not change too much, but if you think about the change of the crystals, that the crystals have to get together, that you might have certain areas of very high temperature, then you will have different effects. But overall, I would say most of the time we will have the same reaction path.
Mm-hmm. So let me ask you then the next question. So at some point you referred to the chemistry happening in the Bolm reactor as accelerated chemistry. So we can refer it in contrast, for instance, let's call it in contrast with a slow chemistry that will happen in just a solid state that will not be in the ball mill. Is it possible to quantify the effect of acceleration in the Bolm reactor with respect to the such a slow chemistry?
Well, you could measure the speed of the reaction, the rate of the reaction. Yeah, so then you would have a number. But this is maybe not what you really refer to. What I meant, I believe, what I expressed was an accelerated degradation process. Yeah, where we look at a slow degradation on the bench in the pharmacy, and we now speed that up to get impurities, which might be relevant for the biological activity. Otherwise, I would say very often we have to realize that we have, you cannot call high concentration because we're not in, the concentration definition requires that you have some kind of solvation, but it's some kind of dissolution, but we don't have this. But we bring the compounds very close together, the closest together that you can imagine. So I believe that this is also contributing to the speed of the protocol. Very often we do processes that require, let's say, overnight or 10 hours in a solvent, and we do it in half an hour. But that might also have other effects, yeah, because if you do it in solution and you heat it up, that's a slow process, whereas we immediately start having the impact of the milling. It's very difficult to quantify.
Mm-hmm. So the next question is, have you considered trying to set up in situ mass solid state NMR?
Oh yeah, we consider this. This is almost a question to my colleague Thomas Wiegand. Now there is one work by Van Wullen who has done this together with Francesca Emmerling. There's one article about in situ NMR, solid state NMR, but that's a very special setup. We at the present stage, and I think I can refer again to Thomas. At the present stage, we don't see that we can really do the garden variety mass spectrometry, MIS NMR technique in situ. So we still have to scratch out our products, and measure them then afterwards. That is sad, and it would be great to have in situ techniques more, but we haven't reached that stage yet.
Mm-hmm. And the last question is that in the examples that you showed, the solid state NMR was used to rather quantify the resulting products. Now, can you envision to use a solid state NMR to get some insights into reaction mechanisms in the solid state?
Yes, absolutely. Absolutely. And in fact, we have the first paper that we have was a bromination of an organic molecule. And in this process, we looked also at intermediates. We wanted to study the pressure effects in the rotors and the whole process. But we see many intermediates and many intermediate stages. So if we identify them, if we make compounds that relate to that spectrum, I think we can very nicely learn about the processes. This is a technique that is wonderful because we don't have to dissolve anything. Yeah, so we take immediately the sample out. We have the solid sample and can analyze it immediately. So that's a great technique for mechanochemistry, I believe. So absolutely, I think we can identify intermediates. We can use that also for mechanistic studies. Absolutely.
Okay, so these are all questions that we got from the audience. So once again, thank you very much for your presentation, and thank you very much for accepting the invitation from the CMCC.
Yes, thank you very much for hosting me so kindly. Thank you very much. Thank you. Bye-bye.
Thank you, Professor Bolm, for outstanding presentation, and thank you very much for joining us. Just to remind you all that all of our previous seminar speakers are available to watch anytime on our YouTube channel, and I encourage you to check them out. We also have some great seminar speakers planned in the upcoming months, and we hope that you will join us for all of them. Thank you again.